right, sound check, sound check. Looks like audio's working fine. Let's see if we have video. Do I see my hand moving there? Give it a second. Yep, I see it. All right, perfect. Then we can go ahead and take off these headphones. And let's get started with what should be the final topic, the final proper lesson for Physics 1, apart from what I mentioned at the end last time, like a sort of review test strategy sort of thing that's going to be for both Physics 1 and Physics C, in which I will actually take care of something I forgot last time. So before the previous stream, there was a problem involving a pendulum in an accelerating elevator, which I said I would discuss the next time and never did. And I feel like it's probably better to save that for whenever I do so after this, I'm going back to Physics C, doing some calculus stuff with them, and once that's all done, we'll do one final episode for both Physics 1 and Physics C that's just going to be going over like some tips and advice for the test and whatnot, and maybe like some common problem types that you'll see and similar examples and whatnot. And I think in that video that would be the best place to put it so that the Physics C students don't miss it, because if I do it here, the Physics C students are probably going to be skipping this, so it wouldn't make sense to put it here. I'll just do it in that video where everybody is going to be watching, well, everybody who's actually committing to watching the whole entire playlist anyway. So yeah, that problem will be taken care of there, not today. What else do I have in terms of announcements and plans for today? I made some corrections. The previous stream, I made so many mistakes that I did not catch during the stream, and I caught them while time stamping. So for those of you who just watched it live or watched it before I got around to timestamping it, you might want to go back and read the pinned comment that I added to the previous part, because yeah, I made a number of mistakes there, or just worded things really poorly, and the pinned comment will point out all the corrections. Also, I added some iCards, which you can find in the top right corner, that were relevant for some of the things that I was mentioning here and there. So that might be something worth looking at as well. That might be another reason to go back and revisit the previous session. And I think that is it in terms of announcements. There aren't too many topics left to discuss here, so this could be a quick one, but knowing me, I will probably find a way to make it go for nearly 5 hours. I don't know why the parts are getting longer, but well, I think I know why the parts are getting longer. It's because I'm finding so few opportunities to do these streams that I subconsciously try to squeeze in as much as possible, because I don't know when the next opportunity will be. And also, it's probably a subconscious attempt at making up for lost time. But anyway, we have, I guess we're just going to start with the problems that I left you with last time. I left you with 2 of them. So the first one was a problem that I made up. And the description of the problem is, we have a 2 kilogram block of wood whose density is 650 kilograms per cubic meter. I did not give its volume, you're not going to need it in this problem, but it is immersed in water to the point where the water level reaches half of the wood block's height. To the point where the water is half of the wood block's height. And then for the rest of the wood block's height, I add some sort of mystery fluid whose density is such that the entire weight of the wood block ends up being supported by the total buoyant force due to the water and this mystery fluid. What is the density of this mystery fluid? That is the question. So if we draw a force diagram for this thing, forces acting on it will be mg, just its own mass, times the acceleration due to gravity, and two buoyant forces. One due to water, force buoyant water, and another buoyant force, force buoyant, I guess, question mark for our mystery liquid. And those need to cancel out to zero. Those need to cancel out to zero. So I can say that the net force on this thing has to be zero, has to equal, I'll do up minus down. So it'll be rho times what volume of water is being displaced? Well, it's half the volume of the wood block, so 1/2 V wood times G plus another buoyant force, so that's rho water. I'll just call it rho W. Actually, no, rho W is because it could be confused with wood, so let's not do that. So rho water times 1/2 the volume of the wood times G plus the buoyant force due to the mystery fluid, so that's going to be rho question mark times it covers 1/2 of the volume of the wood times G, and then minus the mass of the wood times G. Well, the mass of the wood times G, I guess I can just substitute it with 2 kilograms, or I could write it as the density of the wood times its volume, actually. Oh, yeah, you can solve for the volume of the wood since you have its density and its mass, but you don't need it because mg can be rewritten as rho wood times v wood times g. Okay, there we go. And now, since this is a 0 over here, you can divide everything by v wood, and the volume of the wood block doesn't actually matter. And also you can divide everything by g, so the g also doesn't matter. It doesn't matter what planet you do this experiment on. What you end up with is density of water plus density of the mystery fluid minus the density of the wood equals 0. Or rather, half the density of the water plus half the density of the mystery fluid. So 0 equals 1/2 rho water plus 1/2 rho mystery minus rho wood. Add rho wood to both sides. Factor out the 1/2 here, and you've got rho water plus rho mystery fluid. The wood is 650 kilograms per cubic meter. the water is 1,000 kilograms per cubic meter, and that leaves us with just the mystery fluid having an unknown density. Multiply both sides by 2 to get rid of the 1/2. 2 times 650 is 1,300, and then 1,300 minus 1,000. The density of the mystery fluid must be equal to 300 kilograms per cubic meter. Not too terrible. In fact, I thought of a problem, and I want to kind of think through it a little bit more, but if it works the way I'm expecting it to, you might be able to come up with a pair of fluids that are at just the right density where the object in there can start going up and down and up and down, because if you have like the denser fluid on the bottom, which will have a greater buoyant force, versus a less dense fluid at the top, in which the buoyant force is weaker and the object sinks, you could end up in a situation where the object goes down into the water, floats back up, gets into the other fluid, sinks back down, and if you get their ratios just right, I think I might be able to create a simple harmonic motion problem out of that, but I need to think through it a little bit more. I can already see why it wouldn't work realistically, because the fluids would be shifting around, and that will mess it up eventually if you tried to do the experiment in real life. But I think at least if we make some idealizing assumptions, I think it might just work. But I need more time to think about that one before I just give it to you. Maybe I'll do it in like, a one-off video, or maybe actually, you know what I can do? I can do it in like the AP exam review / tips video. Yeah, I could do something like that. Well, I'll think about it some more, and we'll see. Nothing's set in stone yet, but it's definitely something I would like to do if it works the way that I think it will. That's enough of me rambling. Let's move on to the other homework problem I gave you. So the other homework problem I gave you is this thing right here. You've got a spring scale. Hanging from it is a block. That block is also submerged in some sort of oil, and this oil is inside of a beaker or container, and this container rests atop yet another spring scale of the compression variety. So you've got like a stretching spring scale versus a compressing spring scale. And the question is, what is the reading on each scale? That was the question. Okay, so here we actually have 3 objects, so let's draw 3 force diagrams. Here we've got 3 objects, so let's draw 3 diagrams. The 3 objects are the block, the oil, which I guess I'll just draw as this fuzzy thing, and the beaker or container. I think the book called it a beaker, but you can just call it a container and be generic about it. So those are the 3 objects that we have. So on the block, we've got the force of the spring scale, so we've got some sort of spring force exerted upward. We have, of course, the force of gravity exerted downward. So that's m block times g. And we have a buoyant force due to the oil exerted upward, so F buoyant. And I think that is it. Yep, that should be it. I don't see it touching anything else that would apply any force to it. Okay, the oil has its own weight pulling it down, so it has m oil times g. There's going to be a normal force exerted on it by the beaker. I'm going to call that normal force container, normal force cont for short. And because it exerts a buoyant force up on the block must exert an equal amount of force back down on it. So there's the reaction to the buoyant force. And I believe that is it. Yep, that should be it. And then for the beaker has its own weight pulling it down, so m container, or m cont for short, times g pulls down on it. Since it exerts a normal force upward on the oil must react with an equal amount of normal force. So this is normal force container must be equal to this normal force that we had over here. And then acting upward on it would be the spring force of the bottom scale. I'll just call it normal force scale. Normal force scale. You can call it a spring force or a normal force. It's not really going to matter too much what you call it. Come to think of it, I could have called this spring force a tension force if I really wanted to. But yeah, those should be all the forces. Am I missing anything? So block, we've got spring force up, buoyant force up, weight down. Oil, we've got normal force up, weight down, buoyant force down. Yep, that's all adding up. And then for the beaker, we've got normal force or spring force up, whatever you want to call it, weight down, and normal force from the oil down. Yep, I think I've got all of it. So now that we have all this, we know that the net force on each and every one of these objects is 0. We know that the net force on each and every one of these objects is 0. So let's figure out what we do know. We do know the density of the oil, and we do know the density of iron, which is what this block is made of. I don't believe the density of the iron is actually necessary here, since we know its mass. Yeah, I think this is unnecessary information here for now. We know the mass of the oil, the container, and the block. We do need the density of the oil to calculate the buoyant force, but I don't think we need the density of iron for anything. So yeah, let's go ahead and calculate we do need the density of iron because it lets us calculate the volume of the block. Yeah, we need to get the volume of the block because the buoyant force is going to be the density of the fluid times the volume of the block times G. Yeah, we do need the density of iron after all. Okay, so let's go ahead and do that then. Density of iron is equal to the mass of the iron block divided by the volume. of that same block. So multiply volume over to the left, divide density over to the right. Volume equals mass over density. Volume V block equals 2 kilograms over 7,800 kilograms per cubic meter, which is going to be a really tiny number. 2 over 7,800 is, let me write that in scientific notation, 2.5641 times 10 to the negative 4. 2.5641 times 10 to the negative 4 cubic meters. I would have rounded it, but since the digits didn't just keep on going, I think I'd prefer to just keep it exact for now. Okay, so now that we have that, multiply it by the density of oil and G to get the buoyant force. So the buoyant force is going to be 916 for the oil times 2.5614 times 10 to the negative 4 times G is 9.8. Okay, 916 times 2.5614 times 10 to the negative 4 times 9.8. And that is 2.299. I'm just going to round it to 2.30. I'm going to say that's 2.30. And since I used standard units, that should be in newtons. That was one of the mistakes I made last time. There was something that was supposed to come out in pounds force, and I wrote it as newtons. And I think there was also something I didn't actually remember to call out in a pinned comment. There was something I misspelled somewhere. Where was it? There was something I misspelled. Oh, yeah, over here. Pounds per square inch. I don't know why I wrote an S. Well, I can imagine why. I was thinking of writing the word square next, and my brain jumped ahead and wrote the S. So, there you go. That's why I'm not the English tutor. Wait. What did I do? Where? There we go. I got my pages mixed up. Anyway, we got the buoyant force as 2.3 newtons. We can get all of the mg's easily. And then it looks like, well, let me write some net force equations for what we have. So, net force for the block. Net force block needs to be 0, is equal to spring force up plus buoyant force up is 2.30 minus mg of the block, so that's 2 times 9.8, that's going to be 19.6. Okay, and we've already solved for the force in the spring. How about that? And then net force on the oil needs to be 0. So that's going to be normal force due to the container, upward minus, we've got buoyant force downward is 2.30, and minus, we've also got the mass of the oil times G. The oil is 2 kilograms, so 2 kilograms times G, that's 19.6. And And that gives us the normal force between the container and the oil, and that leaves us with net force on the container needs to be 0 equals forces up on it. That would be the normal force due to the scale, or spring force if that's what you prefer to call it. I guess if I had to call them both spring forces, I would call one spring force dilation or stretch, and the other one spring force compression. But anyway, normal force of the scale acts upward minus the normal force between the container and oil, which we can solve for using the previous line, and also minus the mass of the container is 1 times g, so that's 1 times 9.8 is 9.8 newtons. All right, so add 19.6 and subtract 2.30, and the spring scale reading at the top is 19.6 minus 2.3 is 17.3 newtons. 17.3 newtons. That's for the top reading. For the bottom reading, so I would add 2.3 and 19.6 to both sides, and that gives me 21.9. So normal force between the container and the oil is 21.9 newtons. And then plug that in over here, 21.9 minus this minus 9.8. 21.9 minus 9.8 is, let's see, 21 minus 9 is 12, and then 0.9 minus 0.8 is 0.1, so 12.1. Normal force scale is 12.1 newtons. So the scales read 17.3 and 12.1 newtons respectively from top to bottom. Top scale 17.3, bottom scale 12.1. There we go. That's not too terrible unless you have just completely forgotten your force chapter. I did call it the most important chapter in all of physics for a reason. Even now, even at the very end, force is still relevant. Even now, force is still relevant. The one thing that might have thrown some people off is you're not used to thinking of liquids and gases as objects that you draw your force diagrams on, but there you go. Yes, liquids and gases can exert forces. That means forces can, by definition, be exerted on them. Newton's third law guarantees that. Anything that exerts a force must be able to have an equal amount of force exerted on it. And vice versa, anything I can exert a force on must be able to exert a force in turn. That takes care of homework. Now, let's move on to the few topics we have left for today. So last time we talked about fluid statics, the properties of fluids that are not in motion. Today we will take a look at fluid dynamics. We will look at some of the properties of fluids in motion. If you looked at the book and you did the reading sections, you probably came across some stuff that we are not going to cover today, topics like surface tension and capillary action and viscous drag and all that stuff. You can worry about it if you need to take a fluid mechanics course for your engineering major or whatever, but we don't have to do that for AP Physics 1, so we won't. So I'm going to start off by expanding our... Oh, actually, no. There was one more thing. I almost forgot. Before we dig into that, before we dig into fluid dynamics, there was one more thing that I said I would try and re-explain from last time. So I was talking about... Actually, let me go back to the page where I had the drawing. Yeah, over here. I tried to explain this and I wasn't really satisfied with the way that I was explaining it. I wasn't really satisfied with... It just felt incomplete. So I'll just draw a simplified version of this. I'll just draw one of those U-shaped tubes. Yeah, let's revisit the idea of Pascal's principle, how fluid pressure needs to be the same at all points within a fluid that are at the same height. And I'll just do one of these U-shaped tubes for the illustration. And the idea is that if the pressure is the same everywhere, then the liquid levels must reach the same height as well, regardless of even the shape of the tube. Regardless of the shape of the tube. So, if I were to add some pressure on one side or the other, if I were to add some pressure on this side would have to rise. If I were to add some more liquid over here, this would add some pressure, and that added pressure would be added to every single point below this section of the fluid, which means over here, the force acting to the right over here would exceed whatever force is acting to the left over here, since the pressure increase is going to occur throughout this whole entire left section of the fluid. So more pressure here, therefore more pressure times area, therefore more force. That would cause some sort of net flow over to the right until eventually this level goes down to here, and this level rises up. This is something that we can accept intuitively, but how do we accept the idea that the pressure increases due to just adding pressure vertically? How does that also increase the pressure horizontally? Why is pressure the same for a fluid in every direction? That is something that I didn't really explain last time. So an increase, or rather the pressure of a fluid, whether it increases, decreases, or stays the same, the pressure of a fluid can exert a force in every direction at once, is basically the idea. In every direction at once, or in every direction equally, might be a better way to say it. The pressure of a fluid can exert a force in every direction equally. When I measure the pressure at some point within this liquid as rho gh, where h is the depth of this point below the surface, well, rho gh plus the atmospheric pressure, of course. When I say that's the pressure, that's not just due to the, we calculated it as the downward force of gravity divided by the area of this cross section, but that pressure is also the pressure that's felt by the sides of the tube. So the sides of the tube, if they are at this depth, the sides of the tube are experiencing some force, some outward force that's equal to whatever the pressure is at this depth times the area. I guess you would say the area would be, because it's not going to be because there's going to be some height, no matter how negligible it is, there is going to be some height for the fluid over here. If I were to zoom in on it, if I were to zoom in on this cross section, it's not completely flat. It's going to have some really, really tiny height to it. So there is going to be some tiny amount of area over here that is being subjected to this pressure. And I'm saying that this pressure is going to be the same sideways as it is vertically at this point, at this depth. So how do we convince ourselves of that? Probably the best and most convincing way I could go about it is to look at pressure the way that chemistry looks at pressure. In chemistry, we think of pressure as a measure of the collisions of particles within a container. If you have a bunch of particles trapped in a container and they're moving around back and forth in all these random directions, they're just moving around like bumper cars, is what I said last time. They're just zipping and zooming around and colliding, sometimes with each other, sometimes with the walls of the container. If you increase the pressure, if you increase the amount of force from above, for example, if I increase the amount of force here, well, that is going to make it so that there's a greater change in momentum when these particles collide with this upper wall. And that's going to result in them moving faster. And if they move faster, well, then that just increases the number of times, the frequency of their collisions with all of the walls. That's going to increase the frequency of the collisions of these particles with all of the walls. So it's really easy to see from the chemistry perspective, from this collision definition of pressure. But if we weren't to resort to that, if you wanted another intuitive way to think about it, here is what I would give you. If I have, let's just say, if I just have a tube or a glass full of water or whatever, something that's airtight, completely filled with liquid. Completely filled with liquid. I guess watertight would probably be the better term here. Completely filled. And then I push down on it with some amount of force. Okay, well, the liquid isn't compressible. We talked about this last time. And since the liquid isn't compressible, it can't just change its volume and shrink to accommodate this additional force that's being exerted on top of it. So what's going to happen is the pressure at every point within the liquid is going to increase. And if I'm forcing down a liquid that has nowhere to go, it can't go up, of course. It can't go up against a force that's pushing it down, and there's no place for it to go down. What's it going to do? It's going to start trying to move sideways. It's going to try and start moving this way and this way. The liquid particles are going to start pushing on the walls. If you increase the force on them from above, they are going to start pushing harder. Yes, they're going to start pushing harder down, but the particles beneath them are going to just exert a stronger normal force up because they don't want to be crushed by the weight of what's above them. So the layer of liquid sitting above isn't going to succeed in moving down. So there's nowhere to go except sideways, so they start pushing on the container sideways, and the more I increase this force, the more that the sides of the container feel that force. That force does get transferred to the sides of the container, so that's why increasing the pressure of the liquid at any height within the container increases the pressure felt not just by the liquid below this top layer that's getting the increase from this force, but also by the container walls on the sides. I think I could have worded this a little bit better, but hopefully this kind of helps make the idea somewhat more intuitive. Hopefully what I said was enough to drive the point home. And this is why we don't really define pressure as having a direction. I mean, the force that results from the pressure has a direction. It's going to be perpendicular to the area of the surface that the pressure is acting on. So it still kind of makes sense to think of a direction for pressure sometimes, but since the pressure of a fluid is technically in every direction all at once, we don't say that pressure actually has a direction. Pressure is a scalar. We'll see some more evidence of pressure being a scalar later today. Now we can move on to a new topic. So first new topic of the day is, well, expanding the definition of an ideal fluid, first of all. So last time we said that ideal fluids are incompressible and non-viscous. Those were two requirements: incompressible and non-viscous. Well, for fluids in motion, we need to add two more requirements for what an ideal fluid is. So the other two requirements are that they flow steadily, that is, the rate at which they flow doesn't change with time, and that the flow is non-turbulent. Flow is non-turbulent. What on earth does this even mean? You've probably heard the term turbulence before. If you've been on an airplane, maybe your pilot communicated to everybody that it's time to buckle your seatbelts because you're about to hit some turbulence. What does turbulence mean? Turbulence is basically, you could say, the random, unpredictable currents that can occur within fluids, whether they're liquids or gases. So I guess let me see if I can try and illustrate this. So let's say I'm looking at a body of water. And for the most part, the current is moving like this. It curves a bit because, it's the ocean, but let's say the water is moving this way. But you might get a little bit of randomness mixed in. You might get a couple of random swirls here and there. You might get what are called eddy currents. You might get what are called eddy currents or eddies. Just sections of the water where the particles are flowing in a direction that doesn't really align with the majority of the traffic. Like, think of, I guess a good example of an eddy current would be, well, it's not really a good example, but an example nonetheless would be, imagine a car that's just driving, you know, against the direction that the road is supposed to go, and all the disruption it causes while it's going against where all the other cars are moving. You know, all the other cars are moving, sure, some of the cars will crisscross as they change lanes, but for the most part, there's still just one general direction in which the cars are flowing, and then you have this one car that's doing whatever. Maybe it's going against the direction that all the other cars are going, or maybe it's just kind of crisscrossing the lanes in this weird way where it's doing wide turns or whatever. I guess that would be the closest solid example I could give to an eddy current. Just some sort of disruption, something that defies the average flow within a liquid. So eddy currents, or sometimes you might hear them referred to as eddies. These are what you expect to see when the flow of a fluid is turbulent. And of course, you can have low turbulence or high turbulence, or if in the case of an ideal fluid, the assumption is going to be no turbulence at all. So it's not necessarily a black and white thing. Fluids can have turbulence to varying degrees, but we're not going to worry about that. We're going to assume that our fluids are ideal. We're going to assume that our fluids behave ideally. Okay, so now that we have established that, now that we've added two more properties to ideal fluids, let's go ahead and talk about flow rate. Let's talk about fluid flow rate. Pretty simple definition. You could probably come up with it on your own just through using common sense. The rate at which a fluid flows is defined by the volume or mass. There's two different ways you could define it. You could either define it in terms of mass of fluid moving per unit time, how many kilograms of water are moving through this pipe per second, or what we're going to use more commonly is volume of fluid per unit time. Two different ways you could define it. We're going to use volume. This is what we will use the overwhelming majority of the time, but if they throw you a curveball question where they ask you what is the flow rate in kilograms per second, that shouldn't be too hard for you to do. You would literally just take your volume per second flow rate, multiply by the density, and there you go, your volume has turned into mass and you're done. That's really the only difference between the two. But this is what we will use. This is what we will use. We will use this version. Okay, so if I take, let's say, water moving through a pipe, or any other liquid for that matter. So it's in here and it's flowing through a pipe. Then it's going to be moving at some sort of velocity, assuming that the flow is steady and non-turbulent. It'll just move in a straight line. So it's going to have some sort of velocity, little v. And I can actually relate this velocity to the flow rate. If I know how many cubic meters of water are moving in here per second, then I can relate it to the velocity by just looking at the cross-sectional area of the pipe. So what is this area over here is basically what we need. It doesn't matter if the shape of the pipe is circular or rectangular or whatever. The equation stays the same regardless. And if I try to write out the volume of the water within here, if I try to figure out the volume of the water within here, I can say that the volume is equal to, if I were to just to take a small segment of this, let's say I take this segment over here, let's say I have this section that I'm going to highlight, yeah, this section over here. The water moves from this point to this point within some amount of time t, and the volume of water that travels from this point to this point would be just the volume of this disk that I've highlighted. So the volume of this thing would be equal to the area times whatever this width is. Whatever this width is, or I guess I could also call it the height. I'll just call it L. I'll just call it L. I didn't make enough space for this, did I? I wrote this velocity too close, but that's okay. So if I do A times L, if I do A times L, that's going to be my volume. That's going to be the volume of this small section of water that has moved over the course of this time t. Okay, then the flow rate v over t would have to be a times L over t. You just divide both sides of the equation by t. But what is L over t? Well, L is this distance, and if I take this distance divided by the time it takes to travel this distance, oh, that's the velocity. So this L over t, given that L over t is just going to be equal to the velocity, I can say that this is A times V. A times little v equals big V over t. And there we go. So we actually have two equations for flow rate. You can either just do volume over time, or you can do area times velocity. Either one will work. But we can do better than this. If the flow rate is constant, which for an ideal fluid it should be, if the flow rate is constant, then if I have, say for example, I don't know, 10 cubic meters of water moving through this pipe per second, then if I have 10 per second coming in over here, it better be coming out at a rate of 10 per second as well, because if it's coming out slower than it's coming in, then it would be forced to compress. That's not an ideal fluid. An ideal fluid is incompressible. It would have to come out as quickly as it's going in. The number of gallons, liters, cubic meters, whatever volume unit you want to use per second going in has to equal the volume going out per second. It has to, because anything else would just defy the definition of an ideal fluid. So if this pipe branches out or expands or compresses, then something is going to have to change about the velocity in order to ensure that the volume moving per second remains the same. In order to keep the flow rate constant. So if I were to move into a wider pipe, for example, like this, if I were to move to somewhere wider, if the pipe widens at some point, Well, the volume per second moving through here has to be the same as it was over here. It has to come out at the same rate that it's coming in. So if I've increased this cross-sectional area and I want V over T to be constant, then what I have is A times V needs to be constant. That is area in the first part of the pipe, A1, times velocity of the fluid flow in the first part of the pipe, V1, has to equal A2 V2. Flow rate here has to equal flow rate here, and if flow rate is A times V, then this A1 times V1 has to equal this A2 times V2. Since the area has increased, what we will see is that the velocity will have to slow down here. It has to slow down because, well, it doesn't have a choice. If it wanted to go faster, it would need the liquid to come in faster. It would need more liquid coming in per second, but the volume of liquid coming in per second isn't changing. So it has to actually slow down here. And the opposite is true if you're moving from a wider pipe to a narrower one. It would actually have to speed up because otherwise it would get backed up, and again, this would require compression. And liquids aren't very compressible. Maybe with a gas pipe you would have less of a problem. Well, until the pressure went up so high that the pipe itself bursts, but that's a separate problem. So to illustrate this idea and just make it a little bit more intuitive, I have a PhET simulation for you guys to look at, but first let's go ahead and name this. This is called the equation of continuity. The equation of continuity. That's what this is. Or the continuity equation. Same thing. Let's take a look at the PhET simulation that I have for it. Let's go to this. So on the PhET website, of course, you want to make sure that you go down here to where it says compatibility, because it's one of their older ones, and make sure you check this box, because it's not checked by default, and I don't know why. It's like they're trying to hide it. But yeah, it's one of the ChirpJ applications that they have, and once you have that checked, it will show up somewhere down here. Ah, here we go, fluid pressure and flow. Okay, so if we open this up, and go to the flow tab specifically, you have a bunch of dots here. I can just uncheck this box to make them disappear if I want to. I can also click this red button, and this gives me like a more organized collection of dots to look at. Whatever you prefer. Let's keep it with the red dots for now. So what I can do here is I can grab these handles and use them to bend these pipes. There's a limit. It won't let me go down any further than that. But yeah, I can do something like this. And what you see there is, well, the number of dots coming out of the left end per second is pretty much constant. So yeah, the number of dots passing through per second needs to be the same at every point in the pipe. So when the pipe gets narrower, they have to move faster to maintain that rate of flow. It's easier to see with the black dots because they're kind of symmetrically organized. And there it is. So I can also take these measurement devices. I've got this thing measuring speed. Over here it's telling me that the speed is 1.4 meters per second. If I move to the parts where it starts to narrow, I see the speed increasing. Up here it's about 6.4, and then it goes back to slowing down. Also, this is going to tie into something we'll do later. Pressure is about 121, 120-ish. I guess it makes sense that it increases when we go lower, because we talked about that last time. At increasing depth, you have increasing pressure. Let's say we measure it at this height. And so it stays pretty much 118 until you get to over here, where the pressure drops considerably. And then it goes back up again. So when a fluid is moving faster, its pressure is lower. We will get back to that later. What other tools do we have here? I don't want friction, that will mess things up. This flux meter just measures how much flow is going through the area of this cross section, which we can move. The cross section is just some sort of flat circle indicated by this moving ring. And yeah, the concept of flux, it's related to flow, as you can tell. It's not something you guys have to deal with, but the electricity and magnetism students definitely have to deal with the concept of electric flux. So if you plan on doing electricity and magnetism, be prepared to hear this term flux again, but you don't need to know it for Physics 1 or Physics C mechanics for that matter. And I think that's everything I need out of this. We can change the flow rate up here. If that's something you want to adjust, you can increase it. And now everything is moving faster, but still fastest where the pipe is narrowest. And you can even move the pipe itself up and down. That isn't really going to make much of a difference. But yeah, you can grab the handles on the pipes themselves and move them around if it pleases you. And there we go. That's it for that simulation. Let me go ahead and I'll refresh the page just in case we need to open it up again. I won't close it just yet. Now then, the equation of continuity. So pretty simple, straightforward. It depends on area, not just radius. So if you're told the radius of the tube or pipe or whatever doubles, then you have to realize that the area more than doubles. It would quadruple because the area would be proportional to the radius squared, if we're talking about circular cross sections anyway. But yeah, fairly straightforward topic. There isn't really much to do here. Also, this is one of those equations where the units you put in will determine the units you get out. So you don't necessarily have to use standard units here as long as you are consistent with the units you choose. If you're given one area in square inches and another one in square centimeters, then yeah, you have to convert one of those into the other. Or if you're given one velocity in miles per hour and the other one in meters per second, you have to convert one of them to the other. But apart from that, you don't necessarily have to convert units. You will just get out, your unknown variable will come out in whatever units you put in for the known counterpart of that variable. Any other comments that I have to make on this? Right. One application to this, I guess, is the Venturi tube, which actually I think I'm going to hold off on that until we talk. Well, I mean, we can transition into the next topic with it. So there's this thing called a Venturi tube. A Venturi tube. I forget if it's supposed to be a capital V or a lowercase v, but a Venturi tube. I feel like Venturi is a name of someone. But yeah, a Venturi tube is basically this device that can be used to measure the speed of a fluid's flow. And it relies on this idea. It relies on the equation of continuity. And it will often have more liquid over here. It'll be connected to pipes over here, which also contain liquid. And you'll see that the liquid level is at a different height depending on the pressure within the tube. We observed earlier when looking at the simulation that the pressure is lower where the fluid is moving faster. So you can actually use this pressure difference between the 2 points to calculate how much faster it's moving here versus here. You can actually get the exact speed. And the way to do that is to use Bernoulli's equation. The way to do that is to use Bernoulli's equation. So let's talk about, before deriving Bernoulli's equation, let's talk about Bernoulli's principle. Let's talk about Bernoulli's principle. Bernoulli's principle simply states what we just mentioned and observed in the simulation. Bernoulli's principle tells us that fluids moving at faster speeds exert less pressure. Fluids at higher speeds have lower pressures. A very, very simple and safe experiment you could do at home for this is to grab a sheet of paper, or maybe just a strip of paper would be easier, and you just hold it like this, let it flop due to gravity, maybe make it a little bit shorter than a whole page, and then just blow air straight, horizontally over it. And you see that the paper actually tries to lift itself a little bit when I blow air above it. If I was using a lighter paper, you could actually see it rise up, but if you don't trust me, just do it at home. Like, take a piece of paper like this, cut it into a thin strip so that it's actually light enough, and you'll see that it gets lifted. Similar to this is why you are supposed to stay behind the line that they indicate at subway stations or train platforms. You're not supposed to get too close to the rails that the incoming train or vehicle is going to be passing through. And the reason for that is because if it's moving at a high speed, then the air around it would have to be moving at a high speed, since it's pushing the air around it out of its way. And that reduces the pressure of that air, And if you're standing too close, then the air between you and the tracks is going to be at a lower pressure than the air behind you, and that difference in pressure would be pushing you towards the rails, and that's just an accident waiting to happen. So yeah, you probably want to avoid that. If you've ever been like just on the sidewalk, maybe a little too close to the road side of the sidewalk, and a car zips by really fast, you probably felt a little bit sucked towards the road. It's the same idea there. That's Bernoulli's principle at work. That is Bernoulli's principle in action. If I were to illustrate the train platform, you've got this train moving really fast, and the air around it also moving really fast. That would mean that the pressure acting on you this way versus the pressure, or rather the force due to the pressure acting on you from this side, this force is greater than this force. If you're standing too close to that train, you're getting pushed in, and if you're lucky, you'll wake up in a hospital. If you're not so lucky, then you won't wake up at all. So that's Bernoulli's principle, but we can go beyond just understanding this conceptually. We actually have an equation for this. So let's see if we can derive Bernoulli's equation. Let's see if we can derive Bernoulli's equation. So let's say I have fluid flowing through a tube, and let's say that the tube moves up to some height like this. And let's say that this tube is, for whatever reason, at some height above the ground. It could be on the ground, but let's say for the sake of a more complete derivation, let's say that this tube starts off a height h1 above the ground and moves up through this pipe or tube to a height h2 above the ground. Now, in order for this to even work, you need to, of course, do some work down here on the fluid in order to push it up with enough force to actually let it make it up here. So there's going to be some sort of pressure being exerted on this side. There's going to be some force on this side exerting some pressure, so there's going to be some force, I guess we'll call it force 1 equals P1 A1. And over here, the area on this side might not necessarily be the same as the area on this side. There's going to be some force that you're acting against over here, force 2, equal to P2 times A2. So some work is going to be done by this force and against this force. Let me think. I feel like I'm forgetting part of this derivation here. What am I forgetting? Let's let's see, work done at point 1 would be equal to F1 times delta x1 work done by force 2 would be negative F2 delta x2 where I guess we would say we would assume that this is being done for a small amount of time delta t. Let's say that this is occurring over a small amount of time delta t in which the fluid moves from this point to this point at the bottom, and over here at the top, similar business for that same amount of time delta t. It might be a different distance depending on whether or not the speed and area are different up here, but from this point to this point, that would be your delta x2. So this over here is going to be delta x1, which I don't think I've left enough room for to write it clearly. Should have made these wider. Let's see if a different color will help. So we'll call that delta x1 and call this delta x2. Yeah, it's not going to be readable, is it? Delta x2. Yeah, that's not readable at all. I'll just write it down here. Delta x2. Okay, at least one of them is readable. I don't think I can squeeze this one down here since there's not that much space there. But I'll scribble this one out since it's not readable anyway. Okay, so if we travel delta x1 in time delta t, what does this do for us? Well, I can rewrite the force, so I can rewrite F1 as P1 A1 delta t, and over here I can rewrite force 2 as P2 A2 times the same delta t, and delta t is gonna be equal to what? It's gonna be equal to delta x over v, right? Because v delta t, velocity times time, is equal to displacement. So v delta t equals delta x, therefore delta t is delta x over v. So delta t for each of these motions will be delta t will be delta x1 over v1 for one of them, and delta x2 over v2 for the other one. And delta x2 over v2 for the other one. Oh, and come to think of it, I forgot my delta x over here, didn't I? F1 times delta x1. Why did I... Man, there is something going on with my brain this week. I have been making all sorts of weird mistakes all week long. Maybe I'm just not getting enough vitamins. Let's see, so F1 delta x1 is P1 A1 times, not delta t, it's times delta x1. Let me rewrite all of this. Okay, I'll do it over here. Work 1 is equal to F1 delta x1 equals P1 A1 delta x1. There we go. And then work done at point 2 over here is going to be negative F2 delta X2 equals negative P2 A2 delta X2. Here we go. And then the delta X is equal to V delta T. Here we go. I knew something felt off. P1 A1 times, this will be V1 delta T equals P2, or negative P2 A2 V2 delta T. Okay, so the total work on the fluid in this pipe over some amount of time delta T is going to be P1 times A1 V1 delta T minus P2 times A2 V2 delta T. Should have made that V a little bit smaller. But A1 V1 and A2 V2, what's that equal to? Those are both equal to the flow rate. They're equal to volume over time. They're both equal to volume over time. So they are both equal to, oh, and forgot to put these in brackets. The delta T is for both of them. So I can rewrite each of these as volume over time. So it'll be P1 times volume minus P2 times volume, all over time, but also times the delta T, so the time just cancels out. So the total work is going to be pressure 1 times the volume minus pressure 2 times the volume. So total work is P1 minus P2 times the volume. Okay, well, what is the volume? It's actually not going to matter here because we don't actually want the total work. What we want is the total work per volume. What we actually want is the total work per volume of fluid pumped through this tube. So work per volume is what I'm actually going to want, but we'll get back to this in a minute. So that's the total work done. And that's the total work done by just external forces. We still haven't accounted for the other force that would be doing work here, which is gravity. This is the total non-conservative work. Yes, we are going to invoke energy principles here. So let me switch colors. And let's see what we can do as far as gravity is concerned. Well, as far as the gravity is concerned, we are going to experience a change in potential energy of mg times h2 at the top minus mg times h1 at the bottom. That's easy enough. And then if I were to use conservation of mechanical energy, or rather in this case we have non-conservation really, the change in mechanical energy equals the work non-conservative. So I actually shouldn't have called this the total work because this doesn't include the gravitational work. This is actually the non-conservative work here, is what I should have called it. But yeah, change in mechanical energy is equal to this non-conservative work. So that is change in kinetic energy plus change in potential energy equals the change in energy due to this work is equal to P1 minus P2 times V. Big V, the volume. So change in kinetic energy, well, that's just going to be 1/2 m times V final squared, or V2 squared as we called it earlier, V2, minus 1/2 m V1 squared. And then the change in potential energy, we already defined that as mgh2 minus mgh1 equals P1 minus P2 all times volume. If I divide everything by the volume, then here's what I'm going to get. I get 1/2 m over volume times V2 squared. Whoops, make that V bigger. Minus 1/2, again, mass over volume times V1 squared. Plus, this is going to be mass over volume, GH2, minus mass over volume, GH1, equals P1 minus P2. Mass over volume. That should look familiar. That is density. That is the density of the fluid. So we don't need to know the volume of the fluid, and since we didn't know mass, that would have been another problem. We don't need to know the mass of the fluid either. We just need to know its density. So 1/2 density times V2 squared minus 1/2 density times V1 squared plus density times GH2 minus density times GH1 equals P1 minus P2. Okay, let's move all the negative terms to their opposite sides. So I'm going to move this and this and this across the equal sign. And what I'm going to end up with is 1/2 rho V2 squared plus rho GH plus, or rho GH2 rather, plus P2 is equal to, these would move to the right, so positive 1/2 rho V1 squared plus rho GH1 plus P1. Or you can write it with the pressure as the first term, kinetic energy per volume as the second term, and potential energy per volume as the third term. If you don't like having the P at the end, you could have it at the front. But this right here, this is Bernoulli's equation. This is Bernoulli's equation. It's really just conservation of energy on a per volume basis, right? We divided everything by volume over here. Bernoulli's equation. It's just the conservation of energy equation per volume, where instead of looking at the energy itself directly being conserved, we look at the energy per volume being conserved. So yeah, pressure is actually a measure of work per unit volume. Work is a scalar, divided by volume is another scalar, so that just gives you a little bit more confidence that pressure is indeed a scalar, despite all of our talk about the direction of pressure. And in this equation, we can see an explanation for the decrease in pressure due to increased speed. If you are looking at a tube where the height isn't really changing, but the width is, so no change in height, we don't need to deal with rho gh1 and rho gh2, h1 and h2 are equal to each other, then over here, what must happen, we know by the equation of continuity that the velocity here must be higher than the velocity here, so if over here we have v1 is some value, v2 is going to be a higher value over here, then we can just use the equation p1 plus 1/2 rho v1 squared. We don't need to deal with rho gh here because the rho gh's are going to cancel, equals p2 plus 1/2 rho v2 squared. We can see if v2 is greater than v1, then v2 squared is greater than v1 squared. So this term over here is much bigger than this term over here, which means the pressure on the left-hand side needs to be bigger in order for these to be equal. P1 has to be greater here to make up for the fact that 1/2 rho v2 squared is bigger on the right-hand side. So the slower that a fluid moves, the higher its pressure. Now we have mathematical evidence to support that claim, instead of just relying on our conclusions from blowing air over paper. Let me have a look at my notes and see if there's anything else here that I need to cover. Okay, so we can derive something from this, which is Torricelli's theorem. I don't honestly think you need this as a separate thing. It's just a special case of Bernoulli's equation, really, but they highlighted it in the course and exam description for AP Physics 1, so fine. Torricelli's theorem. Here it is. Torricelli's theorem basically says, what if you had, for example, a tank full of liquid, let's say water as our classic example, and there's an opening in it that the liquid can flow out of. So here's some liquid in here. And let's say this liquid starts flowing out. What would its velocity be? What would its velocity be down here? So Torricelli's theorem tells us that this velocity would be equal to the square root of 2g delta y, or h, whatever you prefer to call it over here. I'll just call it 2gh. This should look familiar to many of you. We saw something like this in the energy chapter multiple times. So it's basically kind of the same thing that you get, well, no, exactly the same result that you get for dropping an object from rest from a height of h its final velocity would be the square root of 2gh once you do the conservation of mechanical energy equation. Same thing over here. We would say that the velocity of fluid flow at the top of this tank is approximately 0. It's not exactly 0 because this thing is going down as water spills out of it, but the rate at which it goes down is much, much slower than the rate at which it shoots out of this small hole because of its width. Because it's so wide, when let's say 1 cubic meter per second of water flows out of here, it flows out in this really fast, really thin stream, but depending on how wide this tank is, 1 cubic meter of water might be a really, really thin layer that's not even a millimeter thick. So the velocity of the top surface of this liquid going down, it's going down at a very small rate on the scale of millimeters per second, while this stuff is shooting out at probably on the order of tens of meters per second. So we treat the velocity on the surface as being approximately 0. It's not, but that's the assumption we make in order for this equation to be valid. So we say velocity at the top is 0, and then we just apply Bernoulli's equation. So you would do pressure at the top. Let's say it's a sealed container so that we don't have to deal with atmospheric pressure. Let's say that this container has a cover. So this is covered. Actually, I don't think it'll matter if it's covered or not, because if it's... Yeah, actually I don't think it'll matter, because the same pressure would exist outside here as well. It would be atmospheric pressure up here, and it would be the same atmospheric pressure up here. So we would just do, where do I want to stuff this in? We would do pressure at the top plus 1/2 rho v top squared v1 squared plus rho gh equals p2 plus 1/2 rho v2 squared plus rho g, I guess I should call it h2. Okay, and p1 and p2 are supposed to be equal. And then v1, that's supposed to be 0. And rho gh1, that would just be the height. We'll say h1 is the height of the water at the beginning when the tank is full, and then h2 is going to be 0. We'll set it to 0 at the bottom like we typically do in our conservation of energy problems. And then you can cancel a rho on each side. Let me do that in a different color because it's starting to look messy. Or, well, if I'm being honest, I think it was messy from the start. And then you get g times h1, which is just this h, is equal to 1/2 v2 squared. So g times h is equal to 1/2 v2 squared is just this v over here. Multiply by 2, take the square root. There you go, Torricelli's theorem. That's really all it is. Let me see if there's anything else to note about it in my book real quick. Actually, I don't think it's even stated in my book. I think it was in the course and exam description for the course. Yeah, I don't think I see it anywhere in here. Nope, it was in the course description. Okay, let me actually dig it up real quick, just in case I'm missing anything else with how they worded it. Let's see. AP Physics 1, course and exam description. And then Control F, Torricelli. Oh, great. Doesn't want to cooperate with me. Ah, I can't Control F it. Okay, fine. We'll just do it the old-fashioned way, looking through bookmarks, or I don't even know what they're called, the title navigation, the stuff on the left-hand side panel for the PDFs that they now have. Okay, here it is. It says Torricelli's theorem relates the speed of a fluid exiting an opening to the difference in height between the opening and the top surface of the fluid, and can be derived from conservation of energy principles. Derived equation V equals square root of 2g, and they use delta y instead of h, which is fair. It's the same thing whether you use delta y or h, as long as you define it the same. The speed of a fluid exiting an opening to the difference in height between the opening and the top surface of the fluid. Yep. That is it. That's all that they say about it. It's really just a special case of Bernoulli's equation. I don't know why they're stressing it so much, but there it is. So now that we have discussed that, let's take a look at a few applications to Bernoulli's principle and Bernoulli's equation, and then we can do some problems and call it a day. We might actually end early for once. And by early, I mean less than 3 hours. Well, I've got about an hour and 20-ish minutes to make that happen, so we'll see. Knowing me, it'll probably go over 3 hours anyway. Okay, so some common applications to Bernoulli's principle and Bernoulli's equation. Let's start with, how do airplanes fly? Let's start with airplanes. Airplanes and flight. So there's a type of force that we call lift that takes advantage of Bernoulli's principle. You may have been told, or maybe you're hearing this for the first time, but airplanes have their wings specially designed in such a way to create a force that we call lift. So the way that an airplane's wings are designed, they're more curved on the top and flat on the bottom, and what that does is it allows air, when the airplane starts moving against the air, what it does is the air is coming in like this for the most part, unless it's a windy day, in which case the flow of the air is probably going to be a bit turbulent, but let's say it's just a normal day where we don't have to worry about all that. And it's gonna come across the wing, and of course it's gonna try and keep moving to the right, so some of the air will go over the wing like this, and some of the air will go under the wing. The air that can go under the wing can just go unaltered. But the air that has to go over the wing, well, this line of air over here could have just gone straight if it weren't for a few streams of air below it, a few layers of air below it that were forced to go up. So now it's all getting squeezed in and they're all kind of competing for space. So this is basically the same as what we saw with narrowing a pipe. This is going to lead to an increase in velocity according to the equation of continuity. So we have forced the air above the wing to move faster than the air below the wing. That means pressure above is lower than the pressure below. So the force that the air exerts from below the wing is going to be greater than the force that the pressure exerts from above the wing. That difference is going to create a difference in force called lift. That's going to create a difference in force, and this difference in force, we call it lift. Now, let me introduce you to a little problem here. Airplanes can fly upside down. Airplanes can fly upside down. How on earth does that even work? Because if you take this upside down, well, now the bottom side is the one that has the fast-moving air and the lower pressure. So wouldn't the design of an airplane's wing actually push it down and make it fall out of the sky faster if it turns upside down? Well, the explanation for this apparently is the angle. If the pilot adjusts the angle of flight, they can't fly perfectly upside down, but if they adjust the angle of their flight, they can make it so that they can still manage to fly upside down. If they fly upside down at an angle, so here's the curved part of the wing and then there's the flat part. If they fly at an angle instead of being completely upside down, we're looking just from the side of the wing, by the way. I think I forgot to mention that. You're looking from beside the plane. But if you adjust the angle of the wing like this, then you can create a situation where basically the air is getting deflected downward, and because the air is getting pushed downward by Newton's third law, it would have to push the wing upward. So that is how the airplane would create lift in the upside down flying scenario. It just needs to not fly completely upside down. So there you go. That is how airplanes take advantage of Bernoulli's principle to achieve lift. Of course, the airplanes need to pick up a certain amount of speed in order for this pressure difference to be significant enough to create lift. Airplanes can't just magically take off from zero. They need to pick up speed. That's why they have that long runway track. They need to speed up, they need to reach a certain velocity in order for this pressure difference to be good enough to allow the plane to lift off. But there's one application of Bernoulli's principle. Now we can use Bernoulli's principle in the exact opposite direction. So let's take a look at race cars. Let's take a look at racing cars. You've probably seen racing cars have this thing on the back sometimes that's sticking out of them. Here are the wheels. I guess I won't be able to draw the wheels behind, but that's okay. Racing cars tend to have this thing over here in the back, this spoiler over here in the back. And what does this thing do? What does this little piece in the back do? Well, it basically achieves the exact opposite of what the airplane's wing shape sets out to achieve. It causes the air to move slower below it as compared to above it. So what the racing car tries to do is it tries to create more force downward on it. It tries to create a net downward force that is often literally called the down force. Speaking of race cars, that sounds like a car in my neighborhood doing some... No, wait, that's not a race car. What is that sound? Some sort of lawnmower? I don't even know. I'm sure the microphone is picking that up because I've heard similar things in the background while reviewing some of the older streams. Ah, the beauty of live streaming. Anyway, so these spoilers on racing cars aren't just there for show. They actually do achieve a similar effect to what airplane wings do, except just take this image and flip it upside down. It creates a scenario where there's more pressure above the car than below it, and what that allows the car to do is get more friction. The more downward force there is, the more normal force that's needed to keep the car above road, and increasing that normal force will increase the friction force. And why do we want to increase the friction force? You might remember from uniform circular motion, a car will turn more easily when there's more friction, because friction is what typically supplies the centripetal force needed in order to stay on track. Net force is often going to be the friction force, and if the curve is banked, which isn't too unusual for a race car track, then it'll be some component of friction plus some component of normal force. So actually, even without friction, just the increase in normal force, if the curve is banked, that already is a benefit because it would increase the normal force component that pushes the car towards the center of its turn. So yeah, increasing friction, increasing traction is probably the term that people who don't know physics would say. That's racing car spoilers and the quote-unquote downforce. Okay, 2 more applications, I think, or maybe 3. Oh, actually, going back to airplanes, I forgot to mention this. Airplane pilots need to monitor the speed of the air, so they require a device that allows them to do that while they're in the air. And a lot of airplanes are equipped with this device. It's called a pitot tube. Pitot tubes. So the way pitot tubes work is, well, I'm going to draw 2 different types of this thing. I'm going to draw like the official design and the design that's easier to explain. So one design is going to be like this, where you've got two tubes connected to each other. This one doesn't necessarily have to be wider than this one. I just happened to draw it that way. And if this device has some sort of liquid sitting in here, then what's going to happen is you're going to have this liquid, of course, is going to be experiencing some sort of pressure. And the pressure is typically higher on this side than it is on this side. So you'll see that the liquid level rises higher up here due to less pressure from the air up here. So this is going to move just like the airplane wing. It's going to move against the air. And what's going to happen is over here there's going to be basically a dead zone. The air is going to try and move away from here. It doesn't want to go directly into this tube, so it's going to divert away from this little tube over here. So the air velocity is very approximately 0 over here, because most of the air is just going to curve and move around it. So this is where the airflow is approximately zero and where the pressure is the highest it can be, whereas this other tube is going to be facing air that is moving at some sort of high velocity. So there's going to be a lower pressure in this upper tube, which leads to this difference over here. And then the device is set up in such a way that this height gets measured and some sort of calculation can be done by the machinery there based on Bernoulli's equation to calculate what that pressure difference is. It allows you to calculate the pressure of the air and the speed of the air, if I'm not mistaken. Well, I think you would measure the pressure with a separate device. I think I would have to review the Wikipedia page on pitot tubes to remember exactly how they worked. But the important thing is you understand that this is yet another application to Bernoulli's principle that exists. Now, the official pitot tube design actually is more compact than this. So the official pitot tube design takes this little tube and actually has it resting inside of this bigger, wider tube. So you have this bigger, wider tube over here, and then inside of it is this smaller tube. I don't entirely remember what the design looked like. Hold on. Do I still have that page open? I think I do. No, not that one. This one. Okay, yeah, so they are separated. Okay, good thing I actually didn't close that tab. So yeah, this little thing is still going to come out like this, and this big one is going to go around it. And yeah, there you go. It's basically the same thing, except, it's a more compact design. I'm not entirely sure what kind of difference this makes, except maybe, I guess, it removes any possible errors in calculation due to these technically being at different heights. I guess that would be the main benefit, is that it puts the openings of both tubes at the same height. I suppose that would improve the accuracy. But yeah, otherwise it's the same operating principle. Liquid level is going to be higher in the big tube than it is in the small tube, and something can be calculated, measurements can be taken based off of this height difference. So that's pitot tubes. Atomizers and keels on boats. Atomizers and then keels on boats. So an atomizer, I guess you could say, is just kind of like the Venturi tube that I mentioned. Where did I mention it? Over here. I guess an atomizer is a kind of Venturi tube. If you've seen one of those spray perfume cans, or it doesn't even have to be a perfume can, it can be any sort of spray gun thing. It can be any sort of spray gun type thing, really. If you have, like, I don't know, a Lysol spray bottle, that works too as an atomizer. So you have some sort of container, and there's going to be some sort of fluid in here, perfume, Lysol, whatever, and you squeeze the bulb or pull the trigger or whatever the mechanism is, and what that does is it pushes air out through here, and it gives it some sort of velocity, right? It gives it some speed, and that speed lowers its pressure, and the lower pressure up here versus the higher pressure up here leads to some flow from the bottom to the top. Some of this liquid or gas, whatever is in the container, will flow up into here, and that is how you end up spraying it out. That's how it seems to just magically rise and come out of the spout of your spray can or whatever. And I guess the reason it's called an atomizer is because it also sprays this fluid and kind of spreads it out thinly, basically kind of scattering it about and keeping the atoms separate, so to speak. At least that's how I think of it. I don't know if there's some other reason why it's called an atomizer, but that's the best reason I can think of. It just, I mean, when we talk about like a society that's made of a bunch of atomized individuals, then that is referring to like a society where there's no cohesiveness and no social connection. So yeah, I think I'm right on the money with that, but that's probably something for me to Google later. Why is it called an atomizer? I think my guess is correct in that it has to do with the fact that it's basically spreading the fluid out into nearly individual atoms. But I could be wrong. So yeah, that's the atomizer, which is kind of like a Venturi tube in the way that it works. It creates some increased speed. Oh, I forgot to mention that actually. When you do squeeze this thing, over here, this part, at some point, maybe you can see it, maybe you can't see it, maybe the way that the device is designed, you can't actually look inside of it. But if you could, if you sliced one of these open, I believe what you would see is like a wider tube going into a narrower one and then going back into a wider one, where the narrow part is above where the rest of the fluid sits, in order to get that maximum speed, in order to get that maximum pressure difference to make this stuff go up. But yeah, we will look at a problem involving one of these things later. I know I had one in the book that I wanted to do. So that's the atomizer, and then keels on boats. Keels on boats. So boats, in addition to taking advantage of their sails, sails kind of work the same way that airplane wings do, or spoilers on racing cars. Sails kind of have a bit of a curved shape to them on one side versus the other side that tends to remain flat. That helps create a pressure difference that helps the boat riders direct the boat in whichever way they want to go. But also boats have this fin thing called a keel. Boats also have under the water, so here's the water, and under the water they have this fin-shaped thing called a keel. And this also kind of takes advantage of what airplanes and spoilers do, except a keel is completely symmetrical. So the way a keel works is when the boat tilts and creates an angle, that's where the keel creates two separate sides under the water, where on one side the water is flowing faster and on the other side the water is flowing slower. And what that difference in pressure due to different water speeds does is it allows the water to push the boat, to tilt it back and correct it so that it doesn't tip over. So if I were to look at the boat from this side, if I were to look at it from the perspective of someone that the boat is headed towards, if I were to look at it from this point of view, So here's the front of the boat coming at me. And then I guess, I don't even know if I'd be able to draw the sail properly, but something like that is what the sail would look like coming at me. And then if I could see, if the keel was long enough and I could see it underwater, if this boat were to tilt one way or the other, yeah, I've drawn, oh God, I've drawn this really poorly. Yeah, that's not a very good looking keel. Okay, well, let's dumb this down and simplify it even further, to account for my lack of drawing skills. So let's say the boat tipped over this way, for example. Let me draw a coordinate system over here. And here's the water. And let's say the boat tips over this way, so its keel is going to be over here. In addition to a force kind of similar to the lift or down force in planes and race cars, it's going to generate a force similar to that due to pressure differences, due to different flow speeds. It's going to generate a force that pushes this way, but also with its weight, it's going to have a force acting on its center of mass pulling down on it. And if this is your pivot, if this is the axis about which the boat is rotating, then this creates a torque that moves the boat back and rebalances it, moves it back. In this case, it looks like in the clockwise direction. That helps it regain its balance so that it doesn't completely tip over and so that the passengers don't all drown. So that's keels in boats. And ask some sort of boating expert for more information. I tried looking it up, but I struggled to follow because they were using all sorts of like boating terminology like leeward, and I don't even know what the other terms were, and I was having a hard time following them because clearly they are coming at it from like a boating hobbyist or even professional perspective and not a physics perspective. So yeah, I tried, but that's the most I was able to learn about keels in preparation for this. So if you're not satisfied, you can find some videos on YouTube that you might actually be able to follow better than me, especially if you actually have experience with boats, which I do not. Is that everything? Yeah, I think that's everything. Okay, off to book problems. Off to book problems. Let's see what I have. This one I think is simple enough. I don't think you guys need to actually see it, but I'll read it out. It says, water is pumped into a storage tank from a well, delivering 20 gallons of water in 30 seconds through a pipe of 1 square inch cross-sectional area. What is the average velocity of the water in the pipe as the water is pumped from the well? Okay, so we already said flow rate, volume over time, is equal to area times velocity. So you would just want to convert the volume. They gave it in gallons. They said 20 gallons of water in 30 seconds. I would convert the gallons to cubic meters would be the standard units. And then they said the area of the cross-section was 1 square inch. I would convert that to square meters, and that would get you your velocity in meters per second. But yeah, that's a pretty straightforward problem, so I'm not really going to do it. I don't think you need to see me working that problem. This one says calculate the mass flow rate in grams per second of blood, which has a density of 1 gram per cubic centimeter, in an aorta with a cross-sectional area of 2 square centimeters if the flow speed is 40 centimeters per second. And then part B, assume that the aorta branches to form a large number of capillaries with a combined cross-sectional area of 3 times 10 to the 3 square centimeters. What is the flow speed in the capillaries? All right, so first they said calculate the mass flow rate in grams per second of blood. They said the density of blood is 1 gram per cubic centimeter, so basically the density of water. 1 gram per cubic centimeter is just the density of water in other units. So much for blood being thicker than water. In an aorta, that's just a type of blood vessel for those who don't know their biology. Aorta. You can look it up on Wikipedia. It's like it's that one big blood vessel, I think, that pumps blood directly from the heart into the blood veins, if I'm remembering correctly. Anyway, cross-sectional area is 2 square centimeters, so I'll call that A1 is 2 centimeters squared. And the flow speed, V1, is going to be 40 centimeters per second. V1 is 40 centimeters per second. Well, since everything is in centimeters, I don't really need to convert here. So they wanted the mass flow rate. They want m over t. M over t is just going to be equal to v over t times the density. Volume times density equals mass. Big V. And v over t is equal to, well, area times velocity, so we can just do m over t equals v over t times density is a1 v1 times density, and there we have it. Just multiply those numbers together and we will be done. So we've got 2 square centimeters times 40 centimeters per second. That's going to be 80 cubic centimeters per second, and then times grams per cubic centimeter. Cubic centimeters will cancel out, and yes, we get grams per second. The units do work. And fortunately, the density is 1, so yeah, no more steps. It's just going to be 80. 2 times 40 times 1 is going to be 80 grams of blood per second. That was part A of the question. Part B was, where did it go? Assume that the aorta branches to form a large number of capillaries with a combined cross-sectional area of 3 times 10 to the 3 square centimeters. What is the flow speed in the capillaries? So basically you've got your blood flowing through the aorta, and then it branches off into these thinner blood vessels called capillaries, and even though they're thinner, there's a lot of them, so you actually have to take their combined cross-sectional area. But yeah, it branches into lots of these thinner blood vessels, which themselves, I guess, branch out. That's just a very rough illustration of what we're looking at. Yeah, I'm not really good at biology drawings. But if you look up like a Wikipedia article, I'm sure you'll find something better, a better version of what I'm trying to illustrate here. But yeah, just think of it as a tube that branches into smaller tubes, which again branch into smaller tubes, and eventually you end up with the blood flowing through a bunch of capillaries that have a combined total cross-sectional area of 3 times 10 to the 3. So A2 is going to be 3 times 10 to the 3 square centimeters. What is the flow speed in the capillaries? Well, just use the equation of continuity and you're good to go. A1V1 equals A2V2. A1 and A2 are both in square centimeters, so their units will cancel out. V1 is in centimeters per second, so V2 will come out in centimeters per second as well. So we just do, let's see, 2 times 40 equals A2 is 3 times 10 to the 3 times V2 is going to be something really, really small. 2 times 40 is 80. 80 divided by 3 times 10 to the 3. Parentheses 3 times 10 to the 3. And that's 2.67 times 10 to the negative 2. V2, 2.67 times 10 to the negative 2, or 0.0267. It's actually just a bunch of repeating sixes, but anyway, that's in centimeters per second. Okay, that wasn't too bad. I've got 43 minutes to beat the clock. Can I keep this under 3 hours? Challenge impossible. Do we want to do this one? Let me see. Was it one of the ones that I wanted to do earlier? Liquid flows through 2 horizontal sections of tubing. In the first section, cross-sectional area is that number, flow speed is that number, and pressure is that number in the second section. Cross-sectional area is that number. Calculate the smaller sections, flow speed, and pressure. Okay, yeah, let's do this one. Do I have a backside to this? No, I don't. Let's get a new sheet. Okay, so it says a liquid of density 1.65 grams per cubic centimeter. So first thing they tell us is that the density is 1.65 grams per cubic centimeter. Flows through 2 horizontal sections of tubing joined end to end. In the first section, the cross-sectional area is 10 square centimeters. A1 is 10 square centimeters. The flow speed is 275 centimeters per second, so V1 is 275 centimeters per second. And the pressure is 1.2 times 10 to the 5 pascals. P1 equals 1.2 times 10 to the 5 pascals. In the second section, the cross-sectional area is 2.5 square centimeters. A2 is 2.5 square centimeters. Calculate the smaller sections' flow speed and pressure. Find V2 and find P2. Now, I think because the pressure is in pascals, we do actually need to convert everything to cubic meters, I think. But let's look at the units and see if we can get away with, if if we can't get away with not converting, then maybe we can minimize the amount of converting we have to do, because that would be a lot of stuff to convert. I guess what we would want to do is, if anything needs to be converted, I would convert the pressure. But I can't see immediately whether or not that's going to be necessary. So first part, finding V2 should be easy. They said it's a horizontal tube, so there's no height difference that we need to take into account when using Bernoulli's equation. And we can just apply the equation of continuity there. There is no height change, at least between here and here. I guess the way it would actually be drawn would be more like this. Yeah, with the smaller section sitting on whatever surface this pipe is laid on. Yeah, that's probably the better way to think about it. But either way, them telling us that they're two horizontal sections of tubing is your hint that there is no height difference you need to take into account when using the Bernoulli equation. So to get V2, we don't even need Bernoulli's equation. We can just use the continuity equation. So the first part should be easy enough. A1V1 equals A2V2. A1 was 10 square centimeters times V1 is 275 centimeters per second equals A2 is 2.5 square centimeters. V2 is currently unknown. 10 over 2.5 is 4. 4 times 275 is 1.1 times 10 to the 3. Let me get out of scientific mode for a second, and that's 1100, right? I knew that without a calculator. Anyway, V2 equals 1100, and that's in centimeters per second. Okay, and then the second part was calculate the pressure. Calculate the pressure. So Bernoulli's equation tells us P1 plus 1/2 rho V1 squared plus rho G H1 equals P2 plus 1/2 rho V2 squared plus rho G H2. That's Bernoulli's equation. H1 and H2 are the same. Since this is supposed to be a completely horizontal tube, no changes in height. So that cancels out. We know V1, we know V2. Now P1 and P2. Actually, not too terrible, I don't think, in terms of the conversion that we have to do. So P1 is in pascals. Pascals are newtons per square meter, but they're also joules per cubic meter. Yeah, I don't see. Let's convert the Pascal into grams and centimeters. So 1 Pascal is 1 Newton per meter squared equals a Newton is 1 kilogram meter per second squared per, and then over meters squared. Meters can reduce, and that's going to be 1 kilogram per meter second squared. Let's convert that. So converting kilograms to grams, 1 kilogram is 1,000 grams, and convert the meters to centimeters. 1 meter is equal to 100 centimeters. So that cancels out the meters, and we cancel out the kilograms, and now we get grams and centimeters, and that should work. So we're multiplying by 1,000 and dividing by 100, so we're just multiplying by 10. So the conversion factor, 1 Pascal, is equivalent to 10, whatever this unit is, 10 grams per meter second squared is the pressure unit that we'd be using here. Centimeter second squared, sorry. Yeah, 10 grams per centimeter second squared. That's going to be the pressure unit that we will use. I guess that can also be called a decapascal if you want. No, wait. No, the other way around. A decipascal. Yeah, 10 tenths of a pascal. Grams per centimeter second squared. If 10 of them are equal to 1 Pascal, then one of them is a tenth of a Pascal. So this is a decipascal. So 1 decipascal if you prefer a more compact unit that's easier to write out. So yeah, we'll do pressure in decipascals. So just multiply this by 10. 1.2 times 10 to the 5 pascals is 12 times 10 to the 5 decipascals. So that's what we'll use. 12 times 10 to the 5 decipascals plus 1/2. That's in grams per cubic centimeter, which will work out for us here. 1.65. And then V1 squared, that's 275 squared, equals P2, we don't know yet, plus 1/2, 1.65, V2 squared is 1100 squared. Okay, and just subtract this over to the left-hand side and we'll solve for P2. So we've got 12 times 10 to the 5 plus 1/2 times 1.65 times 275 squared, and then minus 1/2 times 1.65 times 1100 squared equals a really big number, 264,140.625. So I'm getting P2 equals 264,140.625. This is in decipascals, tenths of a Pascal. If I want to convert this back into pascals, then I would simply move the decimal one space to the left, and that's going to be 26,414.0625 pascals. So we can also say it's 26,414.0625 if I convert it back to regular pascals. Or you can write it as 2.64 times 10 to the 5 pascals. No, wait. Times 10 to the, it would be times 10 to the 4, right? Am I counting these correctly? 2.64. Yeah, times 10 to the 4 is what it would be. 2.64 times 10 to the 4 pascals. No, it's times 10 to the 5. Should have gone with my gut. What am I doing wrong here? No, wait. It is 2.64 because the number in my calculator was back when it was still in decipascals. Yeah, never mind. I was doubting myself for no reason. 2.64 times 10 to the 4, if you want to write it in scientific notation. All right, let's have a look at another one. I remember reading this one, but I don't remember if I liked it or not. It says, when a person inhales, air moves down the bronchus, or windpipe, at 15 centimeters per second. The average flow speed of the air doubles through a constriction in the bronchus. Assuming incompressible flow, determine the pressure drop in the constriction. So they say the flow speed doubles, and they ask us to determine the pressure drop when that happens. And they don't tell us anything about what that starting pressure is, so it's basically going to be the same problem as this. In fact, the only twist here is because they don't tell you the initial pressure, you might feel lost until you realize that a person inhaling air is inhaling air that is at a pressure of, well, assuming they're standing at or near sea level, it would just be regular atmospheric pressure, 1.013 times 10 to the 5 pascals. But apart from that, it's basically the same problem. And you would have to also look up the density of air in your book's data table or Google it. 1.29, I believe it was, in kilograms per cubic meter. So here I would actually just convert the 15 centimeters per second into 0.15 meters per second, since that would be the quickest and easiest way to get the units to match up. But apart from that, it's basically the same as this problem. They don't tell you the density, but you can look that up in a data table, and they don't tell you the initial pressure, but you're supposed to recognize that the initial pressure is just regular atmospheric pressure. Okay, we can skip that one. This one says, oh, some kinematics. How about this? How about this one? Some kinematics. So it says, a jet of water squirts out horizontally from a hole near the bottom of the tank shown in the figure, which I will draw for you. So they have this, I don't even know what it is surrounding it, but they have this cylindrical thing, and then inside of it, sticking out from it, is a glass container with a hole in it, and then they've drawn water spilling out. And they said this in the diagram, it shows as 0.6 meters, and then this height was 1 meter, and then the liquid level, let me use this darker color over here. The liquid level in here they called this H, which I think they're just going to describe in the wording of the problem what it is. They said, a jet of water squirts out horizontally from a hole near the bottom of the tank shown in the figure if the hole has a diameter of 3.5 millimeters. So diameter of the hole is 3.5 millimeters, or I'm going to go ahead and convert that to 0.0035 in meters. What is the height h of the water level in the tank? Okay, so h is the unknown that we're trying to solve for. Got it. Okay, well, first thing we need to do is, actually, why do they even give us the diameter to begin with? Do we actually need it? I wouldn't think we do. Yeah, why on earth are they giving the diameter for this? Unless they intended for us to use one of those other equations that's not required for us to cover in Physics 1. Yeah, I think that's what it's getting at. Okay, I think this might be a problem that requires an equation that you don't need to know. Okay, I think that's what the intention was. Let me look through here real quick. It was... I think this was the one that refers to... Was it Fick's law? Yeah, I'm not entirely sure about this one now that they're mentioning the diameter. They might have intended something else, but if we ignore this, then we can still turn it into a useful problem anyway. You can go ahead and assume that the velocity when it comes out of here is going to be completely horizontal. You can go ahead and assume that the velocity as it comes out of here is completely horizontal. So that's v bottom. It's completely horizontal, which means that Vy at this point is 0. And from there you can just calculate the amount of time it takes to land. And then, yeah, let's just do at least the projectile part of this. So delta y is going to be -1 meter. Delta y is -1 meter. And Vy initial is going to be 0, because initially it's completely horizontal. And we know the acceleration in y is just -g, -9.8 meters per second squared. That gives us enough information to use the second equation of kinematics to calculate t. Delta y equals Vy initial times t, and then plus 1/2 acceleration times t squared, -1 equals, well, that's going to be 0, and then 1/2 of -9.8 is -4.9 t squared. Cancel the negatives. 1 divided by 4.9 and take its square root. And that's going to be 0.45175. I'll round it to 0.452. So t equals about 0.452 seconds. And then from there, we know that delta x is equal to Vx times t. Vx is going to be constant. So that's going to be 0.6 meters is our delta x, equals Vx is going to be whatever this V bottom is, times t we found is 0.452. Divide both sides by 0.452. So 0.6 divided by 0.452 gives me 1.327. I'll just round that to 1.33. So V bottom is 1.33 meters per second. And then from there, I don't know why the diameter is being mentioned, so I'm not entirely sure about what I'm about to do. I'm probably going to post a pinned comment later after I review this part, once I play around with this on my own and see if there was anything I was missing, or if this was really just extraneous information that they didn't even need to mention. Because they do sometimes do that. It wouldn't be the first time they've done it. But yeah, so we're going to do Bernoulli's equation. Tells us P at the top plus 1/2 rho V top squared plus rho G, height at the top is just H, equals P bottom plus 1/2 rho V bottom squared plus rho G. Well, if I set this as my zero height, which is what I did, because otherwise it wouldn't have made sense to call this H. H bottom is just going to be 0. So that's gone. Pressure at the top is atmospheric pressure. Pressure at the bottom, the external pressure that you're pushing against, right? That was how we were deriving, where did it go? That was how we were deriving Bernoulli's equation to begin with. We talked about the force exerted by an external pressure on this side versus the force exerted by an external pressure on this side. We're talking about the external pressures, and whatever this height difference is, it's probably not big enough for the difference in atmospheric pressure between this height and this height to be significant. So pressure top is approximately equal to pressure bottom is equal to atmospheric pressure. That cancels out. And what does that leave us with? The density cancels out. We don't even need to know the density, but they did say it was water. So we could have used 1,000 kilograms per cubic meter if we really had to. And then I can multiply everything by 2, so that leaves me with V. Oh, and V top is approximately 0 as well, so we don't even need that. This is approximately 0 for the same reason that we said it was 0 for, where did it go? For the same reason we said it was 0 over here, because the rate at which the water descends through this tank is really, really, really small compared to the rate at which it shoots out through that tiny hole. I mean, if we really wanted to, if we knew the radius of this thing, of this whole tank, then we could actually just calculate the difference between those two rates. But yeah, approximately 0, really, really tiny, so we can get away with approximating it as 0, and that leaves us with just GH is equal to, or rather 2GH is equal to, we canceled the 1/2, is equal to V bottom squared. So yeah, it's just Torricelli's theorem again, the simple case of Bernoulli's equation. We're trying to find H, so divide by 2G, and we get V bottom squared over 2G equals H equals 1.33 squared over 19.6. is exactly 0.09025. How about that? I mean, I still wouldn't trust this as being super exact because the 1.33 did come from using rounded results. So, yeah, 0.09025, and that is going to be in meters. Yeah, about 9 centimeters. That seems reasonable to me. If this whole thing was a meter and their drawing was to scale, then, well, their drawing their drawing doesn't seem to be to scale, because otherwise this h would be about 1/10 of this, and that's clearly not what I'm seeing from the drawing. Their drawing has it looking like it's about 1/3 of the height of this bottom part. I don't even know. What is this bottom thing? Is it like a container, or... I think it's just some sort of cylindrical platform that the tank is sitting on top of. So yeah, that's what I'm going with for now, but I will look into this and see if there was any real purpose behind them giving us the diameter of the hole. Because I don't feel like they would give us that information for no reason. So there might be a pinned comment in a day or two regarding this once I get around to checking it. Anyway, let's move on to another one. Oh, I'm definitely not going to beat the clock with this. I can already tell. This one's got a large storage tank open to the atmosphere. Yeah, so here's another one where it's... So it says a large storage tank open to the atmosphere at the top and filled with water develops a small hole in its side at a point 16 meters below the water level if the rate of flow from the leak is 2.5 times 10 to the negative 3 cubic meters per minute. Determine the speed at which the water leaves the hole and determine the diameter of the hole. So it looks like the diameter should matter for some reason. Well, I mean, I can see it in this problem because here the diameter helps you with, since you have the flow rate, you could just do, volume over time equals area of the hole times the speed. But we didn't have anything related to that in the previous problem. So maybe it really was just extraneous information after all. But yeah, otherwise 46, well, you can't see it, but the problem we just did over here was problem 45 in my book, and the one I just read is 46. They're both similar to each other, so I think I will pass on this. This one. This one right here. So it's got, I'll start it on this next page. This one has a bit of a twist that's easy to miss if you don't pay close attention to the diagram. It says the inside diameters of the larger portions of the horizontal pipe depicted in the figure are 2.5 centimeters. So they've drawn something like this. And then there's a narrowing over here. And then it widens again. So it's kind of dumbbell shaped. And I drew this part too early, but these are supposed to be directly connected. So there is some liquid over here that is up to, let me actually do this in orange. Actually, no. Orange up there doesn't look good. I remember from looking at previous videos. Let's do a darker color like this. So they have a liquid level. They said it rises to 10 centimeters over here. (10 centimeters), that's cm. And then this over here, they said it rises to 5 centimeters high. And if you don't look at this carefully, you might think that the bottoms of these two are in the same place, but they're not. That's something to be very, very careful about. And then, yeah, there's just fluid filling out this whole pipe. Anyway, so it says the inside diameters of the larger portions of the horizontal pipe depicted are 2.5 centimeters. So diameter 2.5 centimeter, 2.5 centimeters for the larger sections, 2.5 centimeters. 2.5 centimeters. Water flows to the right at a rate of 1.8 times 10 to the negative 4 cubic meters per second. So net water flow is to the right, and it flows at a rate, volume over time is equal to 1.8 times 10 to the negative 4 cubic meters per second. Determine the inside diameter of the constriction. Determine the inside diameter of the constriction. Determine this. Determine what this inner diameter needs to be. So here we need to use the Bernoulli equation and the continuity equation all together, it looks like. So let's see what we can do. So this is 10 centimeters from, I guess it would be 1.25 centimeters above this center line. So I'm going to draw this sort of central line over here. And then this water level, or whatever this liquid is, did they say it was water? Yeah, they did say it was water. So if we need to plug in the density, we can. So they said this was 10 centimeters above this height. So this is 10 centimeters above 1.125 from the center. If I were to calculate the actual radius here, half of 2.5, half of the diameter is 1. Did I say 1.125? 1.25 centimeters. And then, oh, I guess my drawing then is, yeah, my drawing is definitely not to scale, huh? Their drawing wouldn't be to scale either. Yeah, their drawing isn't to scale. What is this? They didn't even try. Okay, so definitely not to scale. Heavy emphasis on that, not to scale. I mean, I always say don't assume my drawings are drawn to scale, and this is why. Let's see, so that's 10 centimeters above this mark. This thing is 5 centimeters above this central mark. We don't know what this is yet, so whatever this is, I guess we'll say, let's define some variables. So R1 is equal to the 1.25 centimeters, or we can also call it 0.0125 if you convert it to meters. And diameter 1, D1, is just 2 times that. It's the 2.5 centimeters, or 0.025 meters that they gave us to begin with. And we want to find D2. We want to find D2. So for that, we need to find R2 is equal to, we don't know yet, D2, we don't know yet. These are what we're trying to find. And then we have 10 centimeters of water above 1.25. So you could say it's a total of 11.25 centimeters above this dotted line that I drew. So we've got, if I set this to be my zero height line, this is going to be 11.25 centimeters above it. This, on the other hand, is 5 centimeters above, well, it's going to be 5 centimeters plus whatever R2 is. And what can I do with that? So this is connected to the fact that the pressure at this point is lower. Because the pressure at this point is lower, the water doesn't get pushed up as far in this segment. That's what that's telling me. So I guess the external pressure, yeah, I guess these would be external pressures that I would just plug into my Bernoulli equation. Okay, I was thinking it was going to be something completely different when I first looked at it, but it might actually be simpler than I thought. Okay, so Bernoulli's equation tells us P1 plus 1/2 rho V1 squared plus rho GH plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. So my H1, if I set this to be my H equals 0 line, then my H, well, actually no, hold on. They're going to be at the same height if I'm just comparing these 2 points. These 2 points are at the same height. Yeah, these 2 points are at the same height, so this part cancels out. P1 and P2 are going to be different. So P1 over here is going to be the external pressure of 10 centimeters worth of liquid. Well, no, not 10, 11 rather, 11.25 centimeters worth of liquid. So if I convert that to meters, so basically I'm going to calculate P1. If I'm understanding this correctly, I would just use rho G. I guess I'll call it D this time to not confuse it with H, just using the equation from last time, from the previous stream, for pressure at a depth. Yeah, rho times g times the depth would give me the fluid pressure at this point due to this. So converting the 11.25 centimeters to meters, it would be 0.1125 for D times rho times G. Okay, plus 1/2 rho V1 squared equals P2 is going to be 5 centimeters plus R1. We don't know what R1 is yet. So 5 centimeters or 0.05 in meters. 0.05 plus, did I say R1? R2. 0.05 plus R2 is going to be the depth times rho times G. And then that equals, or no, not equals, plus 1/2 rho times V2 squared. Okay, and then we can, well, I can determine what V1 is because I know the flow rate. So I know V over T is equal to A times V is equal to A1 V1 is equal to A2 V2. So we can do 1.8 times 10 to the negative 4 is equal to, what is the area? Well, the cross sections are circles, so all I have to do is take pi r squared to get the area. So it's going to be pi times r1 squared for the area times v1. And that's also equal to pi times r2 squared times v2. Just solving these two parts for now. R1 I know is 0.0125 in meters, so 1.8 times 10 to the negative 4 equals pi times 0.0125 squared times v1. If I go ahead and divide 1.8 times 10 to the negative 4 divided by, in parentheses, I'm going to do 0.0125 squared and pi, close parentheses, and I'm getting 0.366692989. I'll round that to 0.367. So V1 is about 0.367 meters per second. Okay. So I could plug that in. I don't need the density because all of them have density in them, so the density cancels out. My unknowns are R2 and V2, but that's okay because I have another relationship involving R2 and V2, so I can reduce this to just a single unknown. Yeah, I think I'm on the right track with this. I think I am on the right track with this. So it will be 0.1125 G plus 1/2 of 0.367 squared equals, we are trying to solve for R2, so I would rather rewrite V2 in terms of R2. So that's what I'll do with this in a minute. Equals 0.05 plus R2 times G plus 1/2. Instead of V2 squared, here's what I'm going to do. So pi R1 squared V1 equals pi R2 squared V2. I can cancel the pi's. Pi R1 squared V1 equals pi R2 squared V2 from the continuity equation, so the pi's cancel out, and we can then do V2 equals, actually, better yet, I could have just done this with this. Yeah, that would be better because it wouldn't rely on results that we already calculated. Well, I'll continue with what I have over here, and then I'll write this one separately. So V2, we can write it as R1 squared 0.367 squared, or no, that's V1. R1 squared is 0.0125. Yeah, 0.0125 squared over 0.367, or times 0.367 over R2 squared. That's one possible expression we can substitute for V2. Another expression we can substitute for V2 is we can say pi R2 squared V2 is equal to 1.8 times 10 to the negative 4, therefore V2 equals 1.8 times 10 to the negative 4 divided by pi R2 squared. So another expression for V2 is 1.8 times 10 to the negative 4 over pi R2 squared. Okay, and I think this would be the safer one, since again, it doesn't rely on rounded pre-calculated results. So this is what I will actually use. So this squared, 1.8 times 10 to the negative 4 over pi R2 squared, and then that squared. Oh, this might not be good, actually. This actually might not be good. Because if I'm squaring a square, I don't think this is going to be easily solvable, because that's going to be, if I square this, it's going to become R2 to the 4th, and then I'm going to multiply everything by R2 to the 4th over here, and I'm going to have an equation in R2 to the 4th power and R2 to the 1st power. That doesn't seem like an equation that we would be able to solve. Okay, maybe I wasn't on the right track with this one after all. Yeah, I think I'm going to put this one on hold until I can put some more thought into it. I'll probably record a separate video for this one, because I don't think I'll be able to figure out what went wrong here anytime soon. Okay, well, we'll pass on this. I think I may have done something right here, so I'll hold on to my notes on this page and actually just leave this blank area so I can continue with it later, in case I didn't mess it up too badly. But yeah, let's move on to the last problem that I wanted to do, which was this one. Wait, do I have the backside? No. New sheet. So the last problem I wanted to do was, it says a siphon is a device that allows a fluid to seemingly defy gravity, and then it has a drawing for us. Let me go ahead and copy that drawing. So they have a container full of liquid, And then they say that this thing has some sort of height. Well, the way they drew it, it actually goes lower than the liquid level over here. I'm not entirely sure if that matters, but okay, let's draw it extended. Yeah, this is what I should have drawn. Forget that. Okay, and on their drawing, it says they called this H, and they called this Y. And then it just says the density of this fluid is rho. And over here, they've got some velocity V. So it says a siphon is a device that allows a fluid to seemingly defy gravity. The flow must be initiated by a partial vacuum in the tube, as in a drinking straw. Part A says, show that the speed at which the water emerges from the siphon is given by V equals the square root of 2gh. That shouldn't be too surprising for us. And then for what value of y will the siphon work? Show that the speed at which the water emerges from the siphon is given by V equals 2gh. Oh, wait a minute. Actually, I think h is the way they've drawn this diagram is confusing. So what they've done is they've drawn some lines. They've drawn a line here, and a line here, and a line here. And then they've drawn, there's an upward arrow below this line, and then a downward arrow pointing down to this line, and then an upward arrow pointing to this line. And then the h is written over here. So I think what they actually mean by h is this gap. Yeah, I think this is what they actually meant by h. That would actually make sense. Okay, well, this is the same result we've seen before with Torricelli's theorem. It shouldn't be too surprising to you. If we just use Bernoulli's equation, we get, let me switch colors here. This isn't going to look like that much of a switch, but I swear they're different colors. P1 plus 1/2 rho V1 squared plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. So H2, I'm going to say this is my zero line. This is my zero of potential energy, so that's going to be my H equals 0. So H2 is going to be 0 because I've defined it that way. P1 and P2 are the external pressures at this point and this point. That's just atmospheric pressure. So that's going to cancel out. And then V1, the speed at the surface here, is going to be 0. We've been through all this reasoning before. And that leaves us with the density cancels out, so that's gone. And we get GH1, H1 being just this H that they gave us over here. If we set this to 0, then H2, or rather H1 would have to be just this H that they gave us in the diagram. So we're left with GH equals 1/2 V2 squared. That's the V. V2 is the V that they have in the diagram, so that's equal to 1/2 V2 squared and, 1/2 V squared rather. V2 is equal to that V. And multiply by 2 and take the square root and you're done. How many times have we derived this today? V is equal to the square root of 2gh. I think that's the third time we've done this one today, so hopefully it'll stick. And then the second question is the more important one, which is for what values of y will the siphon work? This y over here. Okay, so new Bernoulli equation. This time I'm going to do it between, I guess between this point and this point is where I would want to do it. So we're going to have P1 plus 1/2 rho V1 squared plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. Let's see. So I'll say my point 1 is over here and my point 2 is over here. So the idea is if this goes too high, then eventually, if you make it go too high, then it'll be high enough that no pressure difference is big enough to pump the water up from here to here. That is the idea. So if you just barely have enough energy to pump the water up to here, then there should be no energy left over for kinetic energy. So V2, the velocity up here, should be very nearly 0. Won't be able to flow, it'll just barely make it. And of course, velocity over here at the starting surface, as we've been doing with this type of problem, we still treat as being very approximately 0. And then H1 and H2. Well, if I redefine this as my new 0 for this part of the problem, I'll say this is my H equals 0 line now. Then this would be at H equals Y maximum is what I would call it. I would call this Y maximum, since that's what we're trying to find. So H1 I've set to 0, H2 is going to be Y maximum, and then P1 and P2. What external pressure do we have here? Well, none. It's inside of the tube at this point. At this point, there would be no external pressure that we're working against. So P2 is also 0. So that just leaves us with P1. What is the pressure at the surface of this liquid? Well, that would just be the atmospheric pressure. So that's 1.013 times 10 to the 5 pascals equals, what's left here? Rho G Y max. Rho G Y max. And divide by rho G, and there you go. Y max equals, I'll just call it P atmosphere over rho G, and you can plug in those numbers if you want to actually know what the value of Y max is, but I think the algebraic steps and the reasoning are the more important parts of this problem. Okay, and that means I've got, what, 2 things I need to double check now? And once I have those figured out, I will either do a separate video going over them if I feel like they need a video, or a pinned comment explaining what went wrong if a written explanation will suffice. If I do decide to do like a second separate video once I figure things out, I will just link it in the description of this video or something like that, probably. Or, well, let me think. I might be able to post it in a pinned comment anyway. I know I've disabled people from posting links in comments because, you know, some people will try to use the comments section to spread malware and that stuff, and I don't want that happening. I know it's unfortunate because sometimes people want to debate things and share helpful things and articles and information and whatnot, but we have to deal with the worst users of the internet, unfortunately. So I don't know if my comments are immune from that restriction or not. If they are, then I might just be able to post the link that way, or I could do it as an iCard. I'm not entirely sure, but just be on the lookout for something in a few days addressing, where did it go? Addressing this especially. And maybe if there actually was something going on with this information over here for this other problem, those will probably be in a video, or at the very least a pinned comment containing some sort of explanation. I would look for the pinned comment first, because if I do end up making a video, I will mention it in the pinned comment and probably give directions on how to get to it. But yeah, this is the conclusion of the course. So as I said at the beginning of the stream, you guys will just now take a break like the Physics C students did. Just hang back for a while until I finish covering some of the calculus topics for Physics C, and then once I'm done with that, for both Physics 1 and Physics C, I'll do like 1 or 2 final streams going over just some strategy tips, and maybe we'll look at a few of the FRQs at the very least here and there, or look at some common problem types. I'll have to think over and probably make some prep notes for what I want to cover, and I will also address that one problem from simple harmonic motion with the pendulum in an elevator that I still haven't addressed yet. So all of that is coming later once I'm done with the calculus topics for Physics C, which will probably take like 2 or 3 more streams. So yeah, skip the next 2 or 3 streams unless you're interested in Physics C for whatever reason. And I'll see you in the probably final stream for this course before the AP exam. And yeah, hopefully this has been a helpful coverage of the material. I know it has gotten pretty bad towards the end. I started making more mistakes, especially with this chapter over here, since I clearly don't have enough experience teaching this stuff. But yeah, I hope it was enough. I hope this helps at least alleviate some of your worries. And yeah, I think that is it. Take care, keep studying, and class dismissed.